So should we store or retrain ML models for data exploration? Let me first tell you about what exploratory data analysis is, and then I'll move on to attempting to answer the question I'm asking in this talk, and I'll finish with some research opportunities. So what is EDA? EDA is stepwise querying. The purpose of whoever is performing EDA is not always known in advance. Users refine their needs as they go along, and generally there are no logs to learn from. So EDA works either manually, so as a user, you could formulate queries and go from step to step, or it could be semi-automated with a next step suggestion based on a utility function. For instance, some of the work I did in the past that appear in the VLDB and www allowed users to provide a data distribution, and then went and found data regions that whose distribution was similar. That's also the case for the work done by Aditya in CDB, where the system goes and finds automatically data regions that differ in their data distribution from an input. EDA could also be fully automated and generate an end-to-end pipeline, generally using reinforcement learning. That's the case for the work that Tova has been doing, Athena, and also some work we did and published last year at VLDB. So generally, EDA is driven by the application of an operation at each step, or by providing data. One can see it as labeling data in the form of user feedback. That's, for instance, the case in the work of Yanlei on aid, where the goal is to learn queries based on data labeling or labeling tuples. It's also the work of David Martin and others, where you provide examples and you sort of query by example. So in this talk, I'm going to be focusing on operation-driven EDA. And more specifically, I'll be exploring the SDSS datasets. So SDSS is a large sky survey dataset that contains images and metadata about many astronomical objects. I'll be focusing on a subset of 2.6 million galaxies with clean attributes. In particular, we're going to be looking at attributes, at 7 such attributes that are commonly used in astronomy. And these are the attributes that our collaborators in an EU project, a European project called iNode have been using. So if you're feeling lucky, you can, of course, just use Google and get a bunch of nice pictures of galaxies out there. But that doesn't really take you very far. At best, it allows you to do confirmatory data analysis where you know precisely what you're looking for, and that's it, you're done. But in general, in exploratory data analysis, tasks vary from finding a very specific set of items. That's the case here of green pea galaxies, which is a very small number, just a couple hundred galaxies that have this shape, looks like green peas, and that have actually been found purely by accident. In fact, SDSS relies on Galaxy Zoo for a classification of galaxies into different types. And what Galaxy Zoo does, it crowdsources the labeling of images by showing an example, for instance, of a spiral galaxy and randomly selecting images from the SDSS dataset and asking the crowd to indicate whether the image has a similar or a different shape, whether the galaxy in this case is a spiral galaxy or not. And completely by accident, crowd workers labeled some images that happen to be green peas. Those attract the attention of astronomers, who then looked into the data, looked into the properties of those labeled images, mapped them into 2D scales with different attributes describing galaxies, and from there, by hand, built the SQL query that finds such galaxies. Another task that one could be after an EDA is to take a tour of the data. So here I'm showing you some example sets of galaxies described with a conjunction of their attributes. These galaxies are more or less, heterogeneous, right? So in the bottom left, we can see very homogeneous galaxies, but in the top right, the galaxies themselves may be heterogeneous. And of course, the number of sets and of item sets that one can build out of this data is combinatorial in the number of attribute values. So in practice, what happens is that astronomers, in particular the ones we work with at the Max Planck Institute in Germany, spend many hours writing and refining SQL queries. In fact, they're very prolific in writing SQL, and I invite you to go to the SDSS website, where there are logs and logs of SQL queries that are very interesting to look at. And so naturally, one can think of automating EDA to reduce human effort in achieving a task, be it finding a specific set of objects, summarizing data, or taking a tour of the data. And so automating EDA has attracted a lot of attention in our community, and in particular, the use of reinforcement learning or deep reinforcement learning for exploratory data analysis has been very popular. And the reason is that you don't really need logs. I mean, what you need is to define the right reward function, train an agent that learns from the application of certain operations at each step, or the application of queries, if you may, at each step. And the agent learns a series of such operations according to some reward function. And the output is a policy that is a sequence of queries. Generally, these are drill down and roll up queries in the space of all possible sets that one may build from the SDSS dataset. So the hypothesis here is that if the right pipeline or the right series of operations is learned for a given task, it could be applied to finding objects of interest in different regions in the sky. So let's look at this a little more specifically, and I'm going to be illustrating a system that we built called DORA. And this system is based on a data model that is that models sets of galaxies, so item sets, as a conjunction of predicates describing the galaxies. And the operators that will be applied to navigate in the space are defined in such a way that they're closed under this item sets data model. So in DORA, we have 4 operators that we define on the basis of interactions with the astronomers with whom we work. And the first 2 here are basically a roll up and drill down. So each operator here takes a set of galaxies and returns up to k sets of galaxies. The very first line is a bifacet operator that is simply a group by, and it drills into a given set. The second one is a bi-superset. So given a set of galaxies, I want to find the k smallest supersets that contain my input set. And then the last 2 are very specific here to this data set. You give them an input set that has a certain So by distribution takes an input set D that has a certain distribution over some attributes that describe galaxies, and goes and finds K sets that are the closest in terms of their distribution for the same attribute. And by neighbors, which is heavily used by our colleagues, is going to take an input set of galaxies and will find will return two outputs here in dashed lines, such that they have the previous, the next smaller, or the previous smaller value for some attribute, and the next larger. So for instance, if you have as input a set of galaxies with a certain density and photometry, it's going to be finding the two sets whose values, say for density, is immediately smaller or immediately larger. Okay, so these are the four sets that we're using within DORA. Okay, and this is the interface of DORA, and let me attempt to show you a quick demo of the system. So in DORA, we train a number of models which correspond to pipelines. So for instance, and then we can load them up here. And in the fully guided mode, what happens is that the system is just going to be loading a pipeline, a pre-trained model, and applying it step by step. And here the user doesn't intervene. The user gets to observe what is being returned. And what happens here is that the individual operations that are chosen by this fully automated, fully guided exploration are displayed one by one with their rewards. The system continues until the pipeline ends. The user may, for instance, choose to pause the exploration and start another one from scratch. Here it is natural that the system starts with a bifacet because it starts with a full data set. So it naturally wants to dive in. Sometimes it chooses to go back and do a superset. There's another mode under which the user may intervene, for instance. So let's see what we can do here. We will restart. We will say, I'm going to be in a partially guided mode. I'm going to train, I'm going to use a pre-trained model and load it. And then the system is going to go on, execute individual operations that are in that model. The interesting thing here is that the user may choose to intervene at any point. So these are the current operator results, but the user may say, the system says, I'm going to be applying a bifacet in the next step. The user may say, no, I'm interested in applying a by neighbors, and intervene with the pre-trained pipeline. And then the user may keep saying that. The user may say, okay, you're also suggesting a bifacet. Okay, here I'm going to just change the input of that bifacet. The system will execute that operation. Okay, there's also a possibility of managing the produced pipelines. I could save a current pipeline. I could load the previously saved pipelines and continue until I decide that I'm done with my exploration. Okay, so that's DORA for you. Now, the questions I'm going to be raising here in this talk is that, great, I can train a number of such pipelines for exploration for different tasks. And what I want to ask is that going to lead to the ability to making EDA a commodity? Meaning that if I'm given a task, an exploration task, I should be able to automatically find a relevant pipeline or a relevant model, apply inference to solve the task, and then return the results, and eventually also how accurate the resulting pipeline is. So how could I do that? I could, for instance, pre-train a number of models like we do in DORA, and then leverage either in MLOps infrastructure or a database to manage those models, meaning to store, retrieve them, compare them, reuse them whenever I need. So what are these MLOps infrastructures? In fact, at VLDB this week, we heard a number of talks about these infrastructures. They're basically systems to version ML models, including their code, data, configurations, and to track the metadata around associated to specific models, whose purpose, of course, is to ease the deployment of those models and their reusability. So basically, every single company has its own MLOps infrastructure with specificity. For instance, MLflow, Databricks has MLflow and allows you to store the models, access them through APIs, and also there is a UI to get some information about the models themselves. Others, allow you to comment on models, retrain them. Azure, for instance, also has a data governance component where you can choose to delete some models to comply with some regulation and so on. The other option is to use a database. So one could use the database to pre-train the models. For instance, do that, pre-train EDA models per task, store the trained models inside the database along with metadata, and then use the database querying to find models on demand. And then whenever a model is retrieved, inference itself could be done within the database. And to enable that, one needs an extension of the query runtime with the benefit, of course, of not having to exfiltrate the data. And in-DB inference is also a hot research topic whose challenges are to incorporate ML scoring as an extension of the relational algebra, and that aims to use the power of SQL query optimization, but also tackle additional optimizations that arise. And so then the algebra can be compiled into an optimized code for different environments and hardwares. For instance, Microsoft has Raven that has an intermediate representation of ML operations and SQL, and integrate that into a single query plan, and Onyx, that is the runtime environment. Okay, so that's great. So if nothing changes, then we're done, right? We're able to pre-train a number of models, find those models on demand, and use an MLOps infrastructure or a database to perform the exploration. But of course, in a world where things may change, we have additional challenges. So what could change? Well, the data may change. The model parameters and hyperparameters may change, but also, and that's specifically for EDA, the operators themselves may change, right? Depending on how expressive we want each operator to be. So let me pause here and say that this talk is advocating a way of thinking that is based on years and years of data management for handling change. In case you're thinking transfer learning, yes, it could be useful for certain tasks, but it's not always useful, and we don't always know why it works. For instance, we showed that when we are looking into learning in a policy to build a program committee, then if you learn an exploration policy on, for instance, a Sigma 2019 PC, you can transfer it to finding the WebDB PC. The inverse does not always work. So we're going to be putting transfer learning aside and coming back to our DB thinking. So what happens when data changes? in fact, there are a number of proposals out there, mainly driven by industry, that are there to manage different versions of data. So Delta Lake, there's great expectations in Python that is based on rules, what to do when data changes. And there is, for instance, Google TFX to compare data sets. So supposedly, if your data has changed, then assuming you know how to clearly identify what the diff is between your initial training set and the set on which you're going to be using your model, this question, is solved. Of course, there are a number of research questions that remain unsolved here, but we're going to say that this option of when change is applied to data, there are already some systems that allow sort of reusability of existing models. So I'm going to argue that the cases where we need to retrain models are generally cases when the model parameters change or when the operators change. And to do that, I'll go into the details of how we built DORA. So DORA is a system that we built for different data sets in different domains that have been given to us by our European partners. One of them is SDSS. And it relies on training policies or training pipelines, exploration pipelines, based on A3C, deep reinforcement learning agent, where the main difficulty or the main challenge is to define the operations, the set of operations, and also craft the reward function. And then, as I showed you in the quick demo earlier, that these models are made available for exploration. So the reward that was defined within DORA combines two dimensions, familiarity and curiosity. And the idea here is that you want to take a tour of the data. So you will be defining a notion of reward. We're defining a notion of reward or training agents on the basis of the fact that we will let them explore new states. So given an input state as I, the application of an operation on that state is going to be generating a set of item sets. And we will be rewarding the agent for finding galaxies or item sets that have a certain familiarity with a target set, a known set, or that go and explore in the space based on curiosity. So these notions of familiarity and curiosity are inspired, they're in fact equivalent to extrinsic and intrinsic reward, and they're inspired from playing games or learning to play a game. So extrinsic reward is going to be rewarding the agent to basically reflect its success, right, in playing a game. In fact, its mapping to exploratory data analysis is to reward the agent when it finds some predefined target items, right? So when we want to train our agent, we're going to be defining a set of targets. And whenever the application of an operation to a state generates items, item sets that contain the targets, the agent is going to be rewarded. So this is why this is a familiarity reward. Of course, this is going to be limited by the knowledge of whoever is defining the target items for the training. The second component of the reward, the intrinsic reward, which is curiosity, is, as I said, based on learning how to play a game. And that is encouraging the agent to venture into new and unexplored states. So when you're learning to play a game, in fact, you want to learn to go through as many unexplored states as possible. and has been shown to be very successful in learning to play a game. That is also the reason why we thought, oh, that could be interesting to see if combining extrinsic and intrinsic reward is useful in the case of exploratory data analysis, where the user does not necessarily always know where to go and what to look for. So more specifically for familiarity, so the way it works is that we use the Galaxy Zoo project that has 170 galaxy types, and we use those types to sample a set of galaxies that would be considered representative for taking a tour in the data, and that set is going to be used for training. And the familiarity is a modified Jacquard index between the sets that are returned by a state, and the application operation to a state, and the target items that are used for training. And the curiosity is quite simple in our case. In fact, when it was applied to games, it's used in a more complex way to recognize features and so on. But in our case, all the features or all the attributes of galaxies are of interest. And so the curiosity of a state is simply the inverse of the number of times I have seen it, to encourage the agent to explore new states, right? So for the task of taking a tour of the data, we can sample galaxies from the 170 types in Galaxy Zoo and build our training set. And what we did is then to train 5 agents for 5 different weighing of curiosity and familiarity. Each agent was trained for 100 hours for about 1,700 episodes. And then we studied the reward evolution. So what are the different policies that we trained? The first one is familiarity only policy, and this is what's been done in the related work. So what you're doing is that you're training agents to find as quickly as possible the objects that are in your training set. But we also, with our reward function, were able to train a curiosity-only agent, so an agent that keeps venturing into new states, and other agents that have different weights for curiosity and familiarity. Okay, and I'm going to be using these 5 policies, or these 5 training settings, to sort of argue for the fact that if when you change the model parameters, you're going to be observing different behaviors. The second aspect that can bring change is EDA operators, right, that will affect the results of the exploration. And I'll have 2 modes, one traditional mode, which is the most common mode that's been used, which is the one that enables just the ability to drill down and roll up in the set of all possible sets of galaxies we have, and the all operator mode that has the 4 operators that we defined. Okay, so just a few plots here. So one, this set of plots shows the reward evolution during training for all the different training variants or training policies that assign different weights to familiarity and curiosity. And the first observation is that the curiosity is more difficult to achieve with traditional. So if you look at the bottom left corner here, we can see that in training, by using just drill down and roll up, the agent does not quickly get to explore the space. Okay, while if I use the all operators, bottom right, I can see that most policies have, anyways, all policies have a higher curiosity reward, right? So what this is telling me is that the set of operators I'm using, or the library of operators I'm making available to my agent, is going to affect my ability to basically jump between different data regions in the space. The second observation, which is equally interesting, is that if I optimize only for curiosity, right? So if I say, okay, I'm doing data exploration, so let me just be curious. So if I optimize only for curiosity, it actually does not help me take a tour of the data. And that is exhibited by the purple line, which is basically the lowest line, say on the left-hand side here. I can see that the familiarity reward of my purple line, both on the left-hand side and the right-hand side. So regardless of the expressivity of my operators, is going to be quite low. Right, so those are the two observations. And in fact, the best results in terms both of familiarity and curiosity are obtained by mixed reward agents. And the second main observation is that if I look at the bottom left here, my histogram is showing me at deployment time. So I've pre-trained already my different agents. And I can see here at deployment time, different tendency to use different operators. Right, so what is, for instance, the familiarity only is really only going to be doing by facet and by superset, while a mix of familiarity and curiosity, like the middle bars, are going to make full use, basically, of the operators that I have. So the agent strategies will differ and depend on the type of reward they seek. And mixed reward agent, work strategically at inference time. Okay. So to summarize this part, the point I wanted to make about model parameters is that for data exploration in general, one needs to optimize for these familiarity and curiosity together, and and that the one needs to be fine-tune sort of these parameters depending on the task or the target, right? So the highest level of familiarity reward are reached by agents with some level of curiosity reward, and that may appear counterintuitive, but that's what the data is showing, right? And of course, this very much depends on the task at hand, whether I'm looking for a needle in a haystack or looking to learn a query or looking to summarize data, I'm going to have to do this fine tuning. The second observation is that the ability of agents to achieve a certain reward is very much dependent on the expressivity of the operators that I have. Some operators may be needed for some tasks and others may not, right? So naturally, when this calls for is retraining, because at inference time, we will have a certain specific goal in mind, a certain task in mind, and potentially also access to a backend or a library of operators that may be different. But the key thing is that this retraining, does not necessarily need to happen from scratch. Okay, so going back to our question, should we store or retrain models for EDA? Well, storing and reusing seems to be a great opportunity, in particular for in-database model management, because it allows to handle changes in data and use the full power of databases to represent the different training sets that are used and compare them and find them at the moment where I need to explore. And additionally, this opens new cross-optimization opportunities at inference time. So optimizations such as model inlining or pushing predicates and so on, especially if we're using an integrated environment for representing ML models and the relational algebra. And the answer of retraining is itself also a great opportunity for guided EDA over relational backends, because it handles changes in model parameters and EDA operators, which we just saw, and of course also opens opportunities at training time. In particular, I could be training for 2 tasks that are not completely independent, a task that will go for full curiosity and a task that will go for 70% curiosity and some familiarity. So there is a potential for having a cross-task optimization by designing composite rewards and using multitasking. But in fact, the decision of whether I should store or retrain should be made by an optimizer, because it should really depend on if I want to go for accuracy or the time or even dimensions such as fairness. And this decision doesn't have to be set in stone at the moment where I start my exploration. It could evolve as I explore data. So if I revisit my problem, I'm given a task that itself may evolve during exploration. I'm going to be finding the most relevant model or the most relevant pipeline, maybe more than one. Apply in-DB inference to solve the task, and that inference may be revisited at each step or at each end steps if I allow the task to evolve, and then return how accurate the resulting pipeline is. In fact, we're building a system to enable such reusability or retraining, or choices of reusability and retraining, where we are revisiting the learning, to have multi-reward optimization, where we have a taxonomy, in fact, of tasks or of policies, so that we could reason over those policies when we're training our models, but also when we are performing the exploration. But today, I'm just going to leave you with a link to playing with Dora and downloading the code if you're interested. Thank you for your attention.